Hi everyone, in today's lesson we're going to talk about a concept called implicit differentiation. So far you've learned what's called explicit differentiation. An explicit function is a function in which one variable is defined only in terms of the other variable. So for example, you've seen y equals this polynomial and you use the power rule simply to take the derivative. So for these two examples we have square roots, so you would raise it to the 1/2 power and then you'd use the chain rule to take the derivative. And we use this type of differentiation when the equation is already solved for y equals. See how all three of these are solved for y equals. Now, a new concept called implicit differentiation, it's a function in which one variable is not defined only in terms of another variable. So for example, this one here is an x squared plus y squared equals 9, where these are all y equals, this is not. Same thing with this one, same thing with this one. Now, some of you might be thinking, well, could I get it in terms of y and then use this? And the answer is yes. But in these particular cases, it would be more difficult to get y by itself, even especially with the trig functions. So when it's difficult to solve for y, that's when you would probably use implicit. And then an application of this is once you find the derivative, you can then use it to find the equation of tangent and normal lines. So let's talk about how implicit differentiation works through an example. So example 1 says, find dy dx using implicit differentiation, and then evaluate dy dx at the point 4, -1. I noticed this says dy dy. It should say dy dx. I don't know why. Maybe I just copied that. So just change that. So dy dx. So basically, how it works is that you're going to take the derivative of each piece separately. So you take the derivative of x squared, and that is 2x. Then you take the derivative of y squared, and you want to treat this y squared as if it was an x squared. So similarly, since the derivative of x squared is 2x, the derivative of y squared is just 2y. But since we've never taken derivatives of y before, we always have to write next to it dy dx. So only if you're taking the derivative of y do you multiply it by dy dx. If you're taking the derivative of x, you leave it alone. So now the reason why you're doing that is because technically, like say in this example, y equals this. When you take the derivative of y, it's technically dy dx, right? That's what we write as our derivative. But technically, the derivative of 1y is 1. So it's 1 times dy dx. So that's why you're taking the derivative of a y and putting the dy dx next to it. And then over here, when you take the derivative of x squared, it's just 2x. You don't actually write anything else next to it. It's just that 2x. So because we're out of order and the y is in the middle, we have to treat it just like we would if it was a regular y. The derivative is dy dx. So let's keep going. The derivative of -4x is -4. The derivative of 5y is simply 5. Same exact concept as if it was 5x. The derivative of 5x is 5. But since we're taking the derivative with respect to y, we must put a dy dx next to it. And then -8, the derivative of a constant is 0. So we don't need to write that. And then bring down the equal sign. And the derivative of this 0 is just 0. Derivative of another constant is 0. So the goal is to solve for dy dx. So what we're going to have to do is move all of the terms that don't have a dy dx to the other side. So we're going to minus the 2x and simultaneously add the 4. So minus 2x and then plus 4. So we have 2y times dy dx plus 5 times dy dx equals -2x plus 4. So again, we got all the dy dx terms on one side. And now what we're going to do is something really unique here. So we're going to take out a GCF of dy dx. And I want you to treat it just as if it was, say, 2ya plus 5a. So notice that I'm just changing this to be an A and this to be an A. The GCF would be, I could take out an A, and when I do that, we're left with 2y plus 5. So it's the same thing. When you do your GCF of dy dx, you pull out the dy dx, divide this term by dy dx, you're left with 2y, and then divide this term by dy dx, and you're left with 5. And then we leave this negative 2x plus 4. And since this is attached by multiplication, the way you get dy dx by itself is divide the 2y plus 5. You don't need the parentheses. So dy dx equals negative 2x plus 4 over 2y plus 5. So that is my derivative. Now you'll notice, because the original function was given in terms of x and y, your derivative is given in terms of x and y. So now the second part says evaluate dy dx at the point negative 4, 1. So what they're asking for is the slope of the tangent line, right? That's what a derivative means, at the point 4, negative 1. So 4 is my x value, negative 1 is my y value. So we can write this dy dx, and I want to evaluate that at the point 4, negative 1. So negative 2, x value is 4. 2, y value is negative 1, and then plus 5. So negative 8 plus 4 is negative 4, and negative 2 plus 5 is 3. So negative 4/3 is the slope of the tangent line at x equals 4, or at the whole point at 4, negative 1. That's it. That's implicit differentiation. Let's try another example. As you can see, these are getting progressively harder, right? So the first problem that I gave you was pretty straightforward. Now the second one's going to be a little bit more challenging. I've put the steps here for you that I kind of went through before. So we're going to do the same thing. We're going to take the derivative of each piece. So the derivative of x squared is negative 2x. Now, the derivative of this is the tricky part for this example, that negative xy squared. The first thing is that this negative is going to probably hurt people. So what I want you to do is anytime you have a product, right, they're multiplying x and y squared, I want you to make sure that if there's a negative in front, you change it to plus a negative. It'll make your life a little bit easier and you won't get the problem wrong. So what you should notice that this is a product rule. So we have to do first times the derivative of the second. So the x, the negative x, is your first, and the y squared is your second. So you can bring down this plus sign, and now we can go from here. So first is negative x times the derivative of the second. Well, the derivative of y squared is 2y. But since I'm taking the derivative with respect to y, I need to write a dy dx. So that's first times the derivative of the second plus second y squared times the derivative of the first. The derivative of negative x is negative 1. And now we keep going. What's the derivative of negative 5y? Positive 5y, 5, and then dy dx. Derivative of negative 8 is 0. Bring down the equal sign. Derivative of negative 2x is negative 2. So it would be nice before we start collecting terms to clean this up a bit. So we have negative 2x. Now this is multiplication. So positive times a negative would result in this thing being negative. And we have a negative x and 2y, so negative 2xy times dy dx. And then we have a plus and a negative again, so that's a negative y squared plus 5 dy dx, and then equals negative 2. So you're going to move all of the terms that are not dy dx to the other side. So we're going to add 2x we're going to add y squared. So add 2x, add y squared. So negative 2xy dy dx plus 5 dy dx equals negative 2 plus 2x plus y squared. So now that all of the dy dx's are on one side, we can take out a GCF of dy dx. When you do your division, you're left with these pieces on the inside. So negative 2xy plus 5. And then you're going to get dy dx by itself. Since they're attached by multiplication, you can simply divide. So I'm not going to write this, like you can if you want. I'm just running out of space. So when you divide, this negative 2xy plus 5 is on the bottom, and this negative 2 plus 2x plus y squared is on the top. So this is my derivative. So that's the first part of the equation. So again, find dy dx using implicit differentiation. We did that. Again, then evaluate dy dx at this point. So I'm going to save this part for you guys to do for homework. Evaluate dy dx at this point. Model it the same way that we did the first example. So do this part now for homework. And then I'd also love for you guys to try example number 3 for homework. Again, these all should say dy dx's. So try that and this one, and we will definitely start class there tomorrow. If you have questions, that's fine, but I want you to at least try this on your own. All right, we'll see you in class tomorrow. Have a good night.